Hello everyone, I'm Qin Huang from Peking University. Today it's my pleasure here to present our paper. This is a joint work from Peking University, Chinese Academy of Sciences, the Chinese University of Hong Kong, and Microsoft Research. In this paper, we address flow level monitoring. We consider a typical network. There are some end hosts in the network, and they are connected by switches. All end hosts and switches can execute some monitoring tasks. There is also a centralized controller in the network to manage all the end hosts and switches. For each packet in the network, we abstract it as a key value pair. The key identifies the flow this packet belongs to, and the values indicate the information carried by this packet. The goal of flow level monitoring is to group packets into flows based on flow keys and compute various statistics such as packet count, byte count, and so on. Network administrators usually hope the monitoring to be highly accurate, and at the same time, they also want to keep the resource usage limited. For full accuracy, we expect the monitoring can cover all time intervals, all devices, and record all flows. And for each recorded flow, we also expect that its statistics are computed with zero error. For resource efficiency, we observe that each type of entities in the network has its unique resource limitations, and we need to avoid resource overload in all of them. For end hosts, they have sufficient memory and their CPUs provide great flexibility to realize arbitrary processing logics. However, we need to control their complexity because the CPU is a bit slow when processing the high-speed network traffic. In addition, end hosts have limited visibility. They have no information about the network internals. For switches, they can process traffic at line rate with the switch ASICs. However, the memory in switches is limited, and there are many restrictions on their programming models. For the controller, it can integrate computational resources of multiple physical machines to form a cluster. It also has the global view of the network. However, the link capacity between the controller and each data plane device is limited, so we cannot transmit too much traffic to the controller. Given the various and tight resource restrictions, existing approaches often make a trade-off between resource efficiency and full accuracy. But different from these approaches, in this paper, our goal is to achieve both resource efficiency and full accuracy at the same time. Before presenting our design, we first analyze the root cause of the resource accuracy trade-offs. We find that existing solutions usually deploy operators in end hosts and switches. This is a common approach to reduce the overheads of the controller. However, the operator in each device is executed individually and lacks of collaboration. For example, an end host cannot control the processing behavior in any switches. In this case, the operator in each device has to contain complete functionalities, including flow key extraction, value updating, and resource allocation. This makes the operators very heavy, so they have to sacrifice accuracy to fit the resource limitation of the devices. These observations motivate us to optimize the two design choices in existing solutions: heavy individual operators and limited collaborations. In this paper, we present OmniMon to achieve both resource efficiency and full accuracy. Our key idea is to redesign the underlying architecture of flow monitoring from a perspective of distributed systems. In particular, we consider the following two questions about the architecture. The first question is how to distribute network telemetry across different entities and coordinate these entities. And second, as in common distributed systems, we need to deal with some unreliable issues, such as inconsistency and message loss. This is necessary to guarantee our telemetry architecture works correctly. We first consider the first question. Our answer to this question is to follow the split and merge principle to propose a novel distributed architecture. We divide the network-wide monitoring into 4 partial operations. Each partial operation is responsible for a piece of monitoring logics. This breaks the heavy individual operators in traditional solutions. Then we coordinate the resources of all network entities to realize these partial operations in a distributed manner. The coordination ensures that the 4 partial operations will eventually form zero-error results, and at the same time, the resource consumption is limited in each device. Since the time is limited, I just briefly introduce these operations here. For flow key tracking, we observe that we only need to record each flow key once in the network. So we record the key of each flow in its source and host. For the second operation, flow value updating, we check flow values in both end hosts and switches. In each device, we allocate some slot of counters to store the flow values. In end hosts, we allocate dedicated slots to each flow because the memory is sufficient in end hosts. But in switches, since the memory is limited, we allow multiple flows to share a same slot. The third partial operation, flow mapping, then determines how a flow associates with its slots. In end hosts, we organize flow keys and slots as hash tables, but in switches, we compute the switch slots by coordinating the controller and end hosts. Since the switches do not calculate the mapping themselves, we embed the mapping information in packet headers and propagate them in the network. The final operation, collective analysis, is performed in the controller. It collects the results from all end hosts and switches to form the final flow statistics. Since the slots at the switches can be shared by multiple flows, collective analysis also needs to restore flow values from the shared slots. Recall that in each end host, we have recorded flow keys and flow values in dedicated slots. So our basic idea here is to decompose the shared slots in switches with the aid of end host information. In this design, no devices will be overloaded, and full accuracy will also be eventually achieved after the collective analysis. Now let's move on to the second question about reliability guarantees. In this paper, our architecture faces 2 challenges from the unreliable network events. First, network monitoring is usually executed based on time intervals, but we do not have a global clock to synchronize time intervals across devices. And second, packet loss is very common, so in some devices, the flow values may not be recorded. We propose 2 mechanisms to address the 2 challenges. For the lack of global clock, we propose a hybrid consistency model to synchronize time intervals. By hybrid consistency, we mean that it's a strong consistency in most of the time, but it will be degraded to weak consistency at some times. For packet loss, we propose a linear system to infer the loss, and we also propose a flow mapping algorithm to make the linear system correctly work in general cases. We build a prototype of OmniMon with DPDK and P4, and we conduct trace-driven evaluations in both testbed and simulation environments. Our experiments include the overheads in different types of entities, the efficiency of reliability guarantees, and the use cases of full accuracy. In summary, we propose the OmniMon architecture with 2 reliability guarantees. We build a prototype and conduct experiments to compare it with 11 state-of-the-art solutions in various aspects. Our source code is also available now, and you may download if you are interested. That's all of my talk. Thank you for your attention.
All right. I was waiting for claps, but there are no claps here. So I think I am looking for questions. I haven't seen any questions coming up. Maybe there is some confusion about where to post the questions. So I guess attendees should feel free to use the Q&A tool over Zoom or the Slack channel to post their questions. In the meantime, I'll ask the question that I have. So in your paper, you have this like critical requirement that the queries have to be answered with 100% accuracy. Like, is this something what network operatives really want? And if not, how will that change the design of your system?
Oh, so sorry, there's something wrong in my network. So can you repeat your question?
Yeah, my question is like, if you don't have to build system that answers queries with 100% accuracy, how will that change the design of your system?
Yeah, if for accuracy, that's a good question. So let me repeat your question first. So your question is that if for accuracy is not required, so how can I change the system design, right?
Yeah.
Yeah. So my question is that if for accuracy is not a strict requirement, and you can relax, and we can relax many aspects in this system. For example, in end host, we do not need to check so many information to guarantee the full accuracy. And in switches, we can use much more aggressive strategies to save the resources. And in the controller, and we can also elevate its workload because if full accuracy is not needed. That's my answer. Thanks.
Okay. So I have one more question from Arun Sharma. So the question is that in this system, do we require compiling these queries on all the network devices, or like, do we need these programmable switches across the network?
Yes, this is a very good question. And currently, our design assumes that we need to modify the network stacks in each end host. But in our paper, we also mentioned that OmniMon also support partial deployment. In partial deployment, we only need to install our end host modules in part of servers. But in that case, only that servers will be monitored, and for other servers, their traffic will be discarded. Thank you.
Okay, so I have one more question. So in your system, is it possible that the network elements change position purpose, or do you assume once a device role is decided, it remains static? So in other words, do you expect the network agents to be dynamically configured, or once you decide a configuration, it remains the same over time?
Yes, in our current design, we assume that the lower of each device is static. So we may extend it in the future. For example, we can also move the flow key checking to the switches, but it may need to sacrifice a bit of accuracy. Thanks.
Okay, I think I have one more question, and we have time for that as well. So the question is that in the beginning of the talk, you characterize the controller as having limited bandwidth, but it seems it's communicating with all of the modules for collective analysis. Is the communication cost not a problem now?
Okay, that's a good question. In my assumption is that the bandwidth for the communication is limited if we want to transfer all traffic to the controller for further processing. But in our design, in the collective analysis, we only need to transfer the partial results from end hosts and switches to the controller. So in this case, the bandwidth is acceptable. Thanks.
Okay, all right. Thank you, Kon, for an excellent talk and answering all these awesome questions.
Okay, thanks, Chun. From the Slack channel, there are already questions. The first question, I think, is the answer to compare with Netseer. And especially, Netseer is also doing the flow level telemetry, but in an event level. And OmniMon is doing the kind of aggregated counter level. So how do you compare with these two solutions?
So sorry, my network has something wrong. So can you repeat the question?
Shortly, so how can you compare OmniMon and the Netseer?
Okay, yeah. OmniMon is actually OmniMon focuses on flow level monitoring, but Netseer is specific for network diagnosis. Actually, OmniMon can detect the packet loss, but we do not identify the root cause for the packet loss. So we just collect such statistics and leave the identify of the type of failures to the administrators. So I think there are two systems designed for different purposes.
Okay, thanks. The second question is, so it's about the scalability of OmniMon. So since that, OmniMon involved and host the CPU, controller, and in your evaluation or in your estimation, so what's the number? What's the size of the network, and what kind of how large is the bandwidth OmniMon can support with reasonable overhead?
Okay, that's a good question. Yeah, actually, the overhead in the controller is very limited in OmniMon. Here, the controller has to do three things. First, the controller needs to compute the allocation of the switch slots to end hosts. But since the network is fixed, so we can compute this information in advance. So there is no overhead in the runtime. And second, the controller needs to help the time synchronization. And in this case, in our experiment, we have evaluated more than 1,000 end hosts in our simulation. And our results shows that the performance remains good, even there are more than 1,000 servers. And finally, the controller needs to perform collective analysis. It collects results from all end hosts and switches. And in this case, the computation is a bit heavy, but we can distribute the computation into different nodes in the controller, because the controller is a virtual node, and it can form multiple physical servers. That's my answer. Thank you.
Okay. Okay. I have one question. First, it seems that you try very hard to use all the available kind of resources to guarantee 100% or near close to 100% accuracy, and collect all the flow counters. I was just wondering what's the use case, or what's the gain, the motivation from that. You use this much of resource and get to the 100 accuracy, and what do you get?
Yes, this is also a good question. Our motivation is that if the measurement is not fully accurate, there may be some interference due to the measurement noisy. For example, if we want to diagnose the network, and the measurement system report that there are some packet loss, but if there are some noise, we cannot identify whether it is really there is really a packet loss in the network, or it's just a measurement error. So if we can achieve full accuracy, we can eliminate such noisy interference due to the measurement. So all the results you observe are actually comes from the network events. So that's our motivation.